You probably use this thing dozens, maybe even hundreds of times a day, without a second thought. But have you ever actually stopped to wonder what's really going on inside your mouse when you flick that little scroll wheel? It seems so simple, but the engineering packed into that tiny device is, well, it's a miniature marvel. So today, let's break down how it all really works. Yeah, this quote absolutely nails it, right? I mean, can you even imagine trying to get through your day without a scroll wheel? Navigating long documents or websites? No way. It's just become the default way we move through our digital world. So that's the big question we're going to tackle. How does that physical spin, that little flick of your finger, get turned into a precise digital signal that tells your computer not just how far to scroll, but in exactly which direction? The answer, as you'll see, is seriously fascinating. Well, it turns out there isn't just one way to solve this problem. For the most part, there are two main methods that manufacturers use, and each one takes a completely different and really clever approach to measuring that rotation. So you've got two teams, basically. In one corner, you have the optical encoder, which is all about playing with light and shadow. And in the other corner, you've got the magnetic sensor, which relies on the totally invisible power of magnetic fields. Two very different paths to get to the exact same goal: a perfect, smooth scroll. All right, let's kick things off with the most common method you'll probably find in your own mouse, the optical encoder. And this one, as I said, is a story all about light and shadow. Okay, so picture this. You've basically got three key players in this little drama. First, you have an infrared LED, which is constantly shining a little beam of light. Second, you have this spinning wheel with a bunch of little slots cut into it. They call it an encoding disc. And finally, on the other side, you've got a pair of optical sensors just waiting to catch that beam of light. So here's the core idea. As you scroll, that wheel spins, and its little spokes chop up the constant beam of light. It's like a tiny strobe light. This turns the steady light into a series of flashes, or pulses. And naturally, the faster you scroll, the faster those pulses get. Okay, so that makes sense for speed, right? Faster scrolling means a faster flashing light. But wait a minute. How does the computer know if you're scrolling up or down? Because a simple stream of on-off pulses looks exactly the same, no matter which direction the wheel is turning. And this is where the genius comes in. Instead of one sensor, they use two, and they place them right next to each other, just slightly offset. Because of this, one sensor will always see the pulse of light a split second before the other one does. So if sensor A sees the light first, the computer knows you're scrolling down. If sensor B sees it first, you're scrolling up. It's that simple difference in timing that cracks the whole direction problem. So if you want to sound super smart, the official engineering name for this setup is an incremental quadrature encoder. The keyword there is incremental. It's called that because it only measures step-by-step changes. It has no idea where the wheel is in its 360-degree rotation. It only knows that it just moved one tick forward or one tick backward. All right, method one is down. Let's move on to the second way to do this: magnetic sensors. This approach is totally different. It gets rid of the lights and the slotted wheels, and instead, it relies on, you guessed it, invisible forces. Now, this whole method works because of a fundamental principle in physics called the Lorentz force. Don't worry, we're not going to get bogged down in the science here. All you really need to know is this. If you have electrons flowing along, a magnetic field can literally push them off course. It can deflect them. So how does a mouse actually use this physics principle? Well, it's pretty slick. They attach a tiny magnet to the scroll wheel itself. And as that wheel spins, the magnet's field passes over a tiny microchip that has electricity flowing through it. That magnetic field pushes the electrons over to one side of the chip, which creates a very small but very measurable voltage. And here's the game changer. By using two of these sensors, they're called Hall effect sensors, and arranging them at a 90-degree angle, the mouse can read those tiny voltage changes in 2 dimensions. This allows it to calculate the exact position of the magnet at all times. This is a huge deal, because unlike the optical method, this is an absolute encoder. It always knows the precise angle of the wheel, from 0 to 359 degrees. Okay, so let's just put these two side by side and recap. You've got two completely different philosophies, right? The optical encoder is kind of mechanical, and it's incremental. It just counts steps. The magnetic sensor is solid state, no moving parts to read, and it's absolute. It knows the wheel's exact position. One is simple and really cost-effective, while the other is generally more precise and durable. So we've totally nailed the digital side of things, how the mouse knows you're scrolling. But what about the feel? That satisfying little bump, bump, bump you get with every tick of the wheel. Where does that come from? Now, the middle click, that's easy, right? It's just a little button hiding under the whole wheel assembly. But that tactile bump, oh, that's where the really beautiful, simple mechanical magic happens. Check out how simple and brilliant this is. There's this little spring-loaded plastic arm called a follower, and it rests against a ring that's covered in tiny bumps or ridges. As you turn the wheel, this little arm just rides up and down, over each little bump. That tiny vibration travels up through the mouse to your finger. And that's it. That's the click you feel and hear. It's so beautifully low-tech, but it works perfectly. Now, of course, these are just two of the most popular ways to solve this problem. In the world of engineering, there's never just one answer. Other designs use totally different methods, things like potentiometers or even electromagnets. Each one is just a different balance of cost, precision, and how durable you want it to be. So the next time you're just mindlessly scrolling through a web page, take a second. Remember the incredible engineering happening right under your fingertip. That tiny little ballet of light and shadows or invisible magnetic fields, all working in perfect sync. The humble scroll wheel is just a perfect example of brilliant design hidden in plain sight. And it really makes you wonder, right? What other everyday objects that we take for granted are hiding that same kind of secret genius?